when they are merging, we can see the effect of these events, like the tidal tails and the beautiful streams, which is observed here. And you can see these objects are really stunning. And I put this title, Dancing Flamenco, because when I saw first time the two galaxies, the major merger happening among two galaxies, in some steps, when we see their step, their tail, the beauty of their tail is like the beauty of the women's when they are dancing flamenco. But yeah, it's just show the beauty of the dancing flamenco and merging galaxy together. But let's see why a study of these structures are crucial for us. Why studying them, stellar streams, tidal tails, it's important for the astronomer. The first thing is because it would allow us to know about how galaxies form and evolve. And in some cases, it will reveal the rule of the dark matter. And if there are a gas-rich major merger, it will give us some insight about a star formation rate. And in some cases, it even can activate the black hole and help to black hole to growth. And but a study of these structures are really difficult because they have many challenges, and we faced during my PhD to all of these challenges, and we've tried to fix them. The first challenge was detecting these complex low surface brightness structures. As you can see here, this is one simulation galaxy, and all of these beautiful structures are created by merger are visible. But after convolving with PSF and adding noise, all of these structures goes into the noise, and it's impossible to extract these structures from noise. It's difficult. And here we've shown some of these, the real galaxies in the universe, and you can see all of them are faint. They have really complex structures, and we need a tool to extract these low surface brightness features from the noise. But during my PhD, it wasn't my main concern because fortunately we use of the tool GenoAstro noise tool, which is one of the tools in GenoAstro and developed by my first supervisor, Mohammad Akhlawi. You can see the arm of this spiral galaxy is really faint, but it could easily extracted from the noise by the noise cell. While by using the old-fashioned tools like Subtractor, some part of this beautiful arm is missed and it torn apart. During the whole of my PhD, I've used the noise cell for detecting these structures, and the first challenge was fixed by using the noise cell. The second problem was a limited spectroscopic coverage we've had during my PhD. Here is the antenna galaxy, and it shows the beautiful tidal tail of these antenna galaxies. And you can see with MUSE, they could just obtain the spectra of the central part and the tail of these antenna galaxies. Even it's just two pointing. Even with several pointing over the galaxies, we cannot obtain the spectra of this structure contiguously. It is restricted. And another challenge which is shown here, we need the pre-selection to know which where we should point the IFUs and obtain the spectra. And we need something to allow us to make some scientific discovery. And while with this pre-selection, we cannot do this blindly looking for the star-forming region in these structures. But fortunately, we have JPAS. JPAS could answer all of these questions. The first advantage of JPAS is that it has 54 narrowbands, and it is imaging surveys, and it will observe all the north hemisphere sky in low resolution. Another advantage of JPOS and in the importance of JPOS is its field of view. Here you can see the field of view of the J plus, but the field of view of JPOS is almost same. It's 1 degree to 1 degree. And this work is done by my colleague Rena. And I put this figure is really beautiful for me because it's compared the other IFUs with field of view of the J plus. If I consider J plus, it's gonna be this size. And you can see all of these local universe galaxy can be observed by J plus. And you can see how much the field of view is big compared to the Khalifa, Muse, and Manga. When first data of JPOS came out, we looked into all the data and we found this beautiful galaxy. And when we compare with legacy survey, we found all of its structures in JPOS is observable. And we call this a galaxy Alba because my name in Spanish means Alba. And then after finding this galaxy, we went into the detail to obtain the spectra of all the streams. But before that, we needed some validation to validate the JPOS spectra. Fortunately, the central part of the Alba is observed by Manga, and then here you can see the spectra of the central part of Manga. And this one is the spectra which is obtained by 54 narrowbands of JPOS. You can see overall the shape of the JPOS SCD is almost same as the Manga. But in some cases, like this emission and absorption is not visible in Manga spectra. To be sure, it is due to the low resolution of the JPOS. We undersample Manga spectra to the JPOS filter set, and you can see the Manga undersample shape is it's almost same as the JPOS, and it was the green light for us to go into the detail of the stellar stream and study them in more detail. Here, I should really say thank you to all of the JPOS teams, to the reduction team, to the engineering, to the scientists, to prepare all of these beautiful data for us. And then after validating this JPOS CD by Manga, I went through the study, I went through the stellar stream. I drew these 4 polygons by hand, and then I obtained the SCD of these structures in 54 narrowbands. When I checked all the lines, this area, it was like the hint for us, because if in the blue and the yellow one, we can see the very weak O3 emission line. And to be checked what is happening, is it a strong emission line or not? We did a tessellation over detection map of the Alba, and then we saw these 2 regions are showing the strong O3 equivalent bits. And when we compare with the Manga, it was exactly aligned with the Manga's footprint. And yeah, it was really interesting, but to be sure how much is these 2 regions is strong, we put these 2 areas and we obtain the SCD fitting, and you can see how much this is stronger to compare to the rest of the SCD. But another issue was we couldn't see the other line like H alpha and H beta. It grabbed our attention, and then we went into the detail to see what is happening for the Alba galaxy. Can we find any other object that have same history as the Alba? Then we found this honey wooer object, which is located near to the IC 2497, as you can see here. And in Galaxy Zoo project, when they were classifying the object, they found this honey wooer object. Then and they wrote a proposal and they obtained the SCD of this object, and they found the O3 of this area, this Honeywover object is 3 times stronger than H alpha and H beta. And when I put all of these stories together, I said maybe because the JPOS has a low resolution, due to this, I cannot see the other lines. Maybe I need to write a proposal and observe those 2 regions by Megara. Then when we study more this Honeywover object, and we found some groups attempt to predict the history, why this object is created. Then I found they are predicting when two gas-rich galaxies are merging, then their quasar is activated, and then it's pull out, it's ionized some gas of the tidal phase, and due to this, Honeywover is created. For me, it was something, when I put all of this together, I said, okay, maybe something same as the Honeywover object is happening to Alba, and due to this, those 2 regions are ionized. But we needed to go into the detail to confirm all of our results. Here you can see the Alba galaxy in O3 filters, and I was in Porto and I did this work with Polis, and thanks to him. With Polis, we obtained the equivalent width map of the Alba, and when we obtained this map, something wondered us. It was wondering with so many rings is surrounded by Alba galaxy. It was big shock for us because we didn't know all of these rings are come from where. We checked the other filters like H alpha and H beta filters, but it didn't happen for them. It was just for this filter. Then, thanks to Mohammed, we went through all the details, all the steps of this data, and then we found in JPOS, when a star is located in one CCD, it goes into the other CCD. And exactly the same problem happened to Alba galaxy in O3 filters. And due to this, I couldn't continue that project. In this step, I really frustrated and I was ashamed to report this issue to the JPOS group because I was claiming I wanna publish the first scientific paper of the JPOS, but I faced with this problem, and it was nightmare. But I didn't give up. I report this issue to all the JPOS. I gave talk. And then I continue my project. But this time I focus on the stellar population of the stellar strings. And now we try to draw the polygons to separate the different shape of the strings to see, can I see any difference between a stellar population of the stellar strings based on their shape or not? And before going through the details of all of these merger remnants, first I needed to for the SCD fitting, I needed Sigale to validate the output of the Sigale SCD fitting. I had manga. Then all the orange dots shows the fluxes comes from the JPOS data. And the orange lines shows the output of the SCD fitting by Sigale for JPOS data. Then for our analysis, we added the SCSS filter. It's the file filter. It shows by these blue triangles. And we even did the SCD fittings by SCSS data. Why we use the SCSS data? Because it has a 5 filter. It is broadband filter, and most of the survey like HSC and LSSD, they are using the same filter set. And on the other hand, we use SCSS because its depth is almost same as the JPOS. Due to this, I didn't focus on the deeper data. And Then we've obtained the output of the C-gala fitting for all the stellar streams, and for the SCSS data, all the fluxes by SCSS is shown by gray triangles, and the JPOS fluxes is shown by colored circle, and the SCD output of the C-gala fitting shows by the lines exactly in same colors. And you can see in most of the cases, like North 1, East, South, and West 2, in radar filters, we found the fluxes in the JPOS is higher compared to the SCSS, sorry, is higher than JPOS, and it is happening due to the bad reduction in SCSS. And on another advantage of the JPOS compared to the SCSS is observable in south region. As you can see, between these two filters of the SCSS, in JPOS we have many narrowband filters, and we can see the output of the C-gala for the SCSS showed many emission lines, while in JPOS we cannot see these emission lines. It is happening due to the broadband filters in SCSS, while it's in JPOS it didn't happen. We had a lot of many narrowband, and it fitted the stellar population properly. And now, after doing all of these processes, we went into the detail of studying the stellar population of the SCSS data, which is shown by orange dot, and JPOS by blue dot. And we can see the main thing here is the JPOS stellar mass is less than the SCSS. On the other hand, the metallicity, which is predicted by SCSS, SCD fitting is much more higher than JPOS, and star forming burst component, like fraction of the burst star forming rate and tau burst, it has much more higher value compared to the JPOS in SCSS. While the Alba galaxy is dry major merger, and we won't expect to see many star forming component. And why? Maybe you ask you why I put here just a stellar mass and the N4000 here. When I draw this corner plot, I was wondering how much of these scattered in each of these corner plot is reliable. To we know which one of these is reliable and how much I can trust them, we define the PS property significant value. This value is defined based on the standard deviation of the property in 6 polygon divided by the median of error bar. And then based on the value of the PS, we exclude all the, not exclude, we didn't consider for our analysis in a stellar population. And then we exclude all the properties that have a PS smaller than 1.1. And you can see if when we sort all the stellar properties, we found just a stellar mass, and the N4000 show us the PS more than 1.5. And if I back here to this plot, due to this, I put a stellar mass and the N4000 here because they show the larger PS in my analysis. And if I wanna tell you about the N4000, the N4000 shows the age of the merger remnants, and you can see, as we predicted, we are assuming the stellar stream has is younger than the central part of the galaxy. We can see these trends in JPOS. While in SCSS, we see the two of the polygons, two of the stellar streams are older than the central part of the galaxy. Yeah, these two regions shows the larger error bars, but still JPOS it's much more closer than what we are expecting in astronomy. And it shows the advantage of the JPOS in extracting the stellar population. Another property which had large value in PS plot was stellar mass. Here you can see the stellar mass which is obtained by JPOS and SDSS. We compared our method, the stellar mass, which is obtained by SET within but two methods by Bell 2003 and Garcia Benito, because most of the people are using these two methodologies to obtain the stellar mass of the object based on the broadband filters. I've used these two heuristic methods, and I obtained the stellar mass of the central part of the Alba galaxy and its merger remnant. And you can see, if we compare these two heuristic methods with these two stellar populations, they are predicting massiver. They are predicting much more massive for these structures. And when we reach to this point, we published this paper, but fortunately the JPOS observing was growth, and I was wondering to check all of these analysis with more galaxies. The IDR came out, but the main problem was it has 12 million detected sources, and I had to know which of these galaxies has merger remnants. And to find them, first of all, I had to exclude all the stars. Because JPOS didn't have the star galaxy separation catalog, I used the SDSS catalog to exclude all the stars from the among all of these 12 million detected sources. Then, after extracting all the galaxy, I put the two criteria on redshift and stellar mass. We choose just galaxies with redshift smaller than 0.1 and stellar mass between 10 to the 9 to the 10 to the 12. And you can see here we had all of these galaxies. Now, in this step, I had to visually check all of these galaxies. Then I wrote the script and I download all the color image from the legacy survey. I use legacy survey because it's deeper than the JPOS and I could see all the stellar stream properly. And then finally, I found these 12 galaxies. This one was really beautiful. This one is the Alba galaxy. I put in my analysis just to increase the number of the statistical study. And here you can see the faint arm. Here is the tidal tail. It is really faint. But the main question maybe is these figures, why they are in red. I found because in legacy survey, when I was downloading the color image, they didn't have, they missed some filters, and due to this, these 5 galaxies are in red. Then I checked all of these 14 galaxies in JPOS, and you can see all the structures are observable. And then in this step, it was nightmare because I had to draw all the polygons by hand, and it took a long time. Then we ran Sigale over all of these polygons. And as you can see here, I put just BN4000 and stellar mass. As we expected, the central part of the galaxy is older and much more massive compared to the merger remnants. Then my main concern was find some emission line among all of these polygons. Then I found, when I was checking visually all of the output of the Sigale, I found this polygon showing the strong emission line in this area. When I checked, it was belong to the central part of this galaxy, this polygon. And while I couldn't see any emission line in other polygons, I was expecting some, maybe the merger between in this merging galaxies, one of them was gas poor while the other one was the gas rich. And due to this, I couldn't see any other emission line in the rest of the polygons. It was my prediction. While in this galaxy, when I check the emission line in the central part and the rest of the polygon, you can see it maybe in some cases it's weak, but it's still visible, the emission line in all the polygons. It shows the time in this merging all the, it was the gas-rich merger. But this is just 14 galaxies, and I can check all of these emission line visually. But imagine if I have 100 of galaxies, and if each one has just 4 polygons, it's going to be really hard. But this polar plot would be useful. Here I showed the merger remnants by orange dots and the central part of the galaxies by blue lines. And some interesting things was here. I could see the trends between DN 4000, which is representative of the age with the metallicity. When galaxies become older, they become more metal-rich. I can see same trends in stellar mass and metallicity, but it's not as strong as the DN 4000 and metallicity. And another interesting is this star forming rate, star formation rate plot. As you can see, most of the merger remnant and stellar central part of galaxy are quenched, and we cannot see any significant star formation rate. While in some cases, like the central part of this galaxy, which shows here, and these 3 polygons shows a strong emission, star formation rate. And when I check the output of the CGALER, it shows exactly the same emission line. This corner plot would allow us to find which substructures has a star forming rate. And another interesting thing in this corner plot for me was the dust, because mostly the dust of the central and the dust of the merger remnant are scattered, while the central part is there. It's just in this area. I was thinking maybe it's due to when merger is happening, they are disrupting the ISM, and due to this, we have this distributed dust. But they are just my prediction. I cannot claim based on the 14 galaxies. Fortunately, JPOS is growing. And then with more than 100 galaxies, I can just confirm all of my results. And it's going, and it will allow me to search blindly for all of these type of major merging remnants. Okay, the second challenge is fixed by JPOS. But what about the third challenge? Accurate reduction and effective PSF subtraction. If I come here, I show the Alba galaxy, which is observed by JPOS and legacy survey. And you can see in legacy survey, due to the bad reduction, all of the merger remnants are missed, and I cannot detect them. Fortunately, we don't have this problem in JPOS. And I can see all the substructure in the JPOS. It's one of the challenges in a reduction of this of the reduction. But because I didn't have this problem in JPOS, I wasn't worried about it. My other concern in JPOS was the brightest star. When I was looking blindly for the major galaxy, I found many of these major merger galaxies is contaminated by brightest star. And I had to exclude all of these from my analysis. And the other one is showed here. You can see it is contaminated by many of these brightest stars. But this problem is not just related to these galaxies. It's even in Alba. We have a bright star here. Maybe its color, it will affect the Alba galaxy. And the PSF issue is not just for the JPOS and J+. As we can hear, in hypersuprime camera, all of these blue areas are masked due to the bright star. And we are missing all of these points in HSC because they are masked. And if we look at the deepest area of the hypersuprime camera, 15% of total area is missed due to all of these bright stars. And if we consider a sky as a cheese, for the scientists, if we mask all of the stars, the sky would be like all of the whole for us. We should discover all of these, we should add all of this area to our analysis, and we need a proper cheese or a proper pipeline. And thanks to the Raoul, he developed a pipeline during his PhD, and you can see he could create extended and non-parametric PSF and subtract it from the SCSS data. And the importance of the subtracting this extended PSF is not just affecting our number count of catalog or adding all of this missed object or stellar stream. You can see even it is affecting the shape of the intra-cluster light, the color of all of the nearby objects. And if I come here, you can see the scatter light of this sky is cover almost the total areas of the coma cluster. We've used the same methodologies as Raoul, and we designed a pipeline for subtracting the PSF from the J plus DR3. But why J plus DR3? My main focus was the J plus. I developed this pipeline for J plus DR3 because when I started my PhD, we didn't have a J plus data. We developed this pipeline for the J plus, and it can be implemented on other savers. And the main difference of this work with Raoul project is in Raoul project, he stacked all the stars, and for each filter, he created one PSF. While in this project, we've tried to create for each exposure different PSF, for each exposure and each filter. Here it shows all the steps for creating the PSF for this exposure of the coma cluster in our SPSS filter. For creating the outer part of the PSF, because we needed bright star and we didn't have enough bright star in each exposure, we used all the exposure were taken 2.5 hours before and after the main exposure. And for constructing the middle part and center part, in each exposure, we had enough star. And we used exactly the same exposure. Then we crop and mask all the extra object, and then we combine all of these stars, and you can see the three part of the PSF is constructed. When you unite all of them together, the final PSF is created. From central part to outer part of the PSF, we can see its surface brightness change almost 15 mag per arc square. And now, if you can see here, the stars is turned off, and it's all the exposures are ready to go and study the low surface brightness science. And here is the scatter light of all of these stars. But designing this pipeline is not as much, it is not easy as much as pressing this button and turning off the light. It had many challenges, and I had to fix all of the problems during my PhD. The first issue was masking the reflection of the mirror automatically, because this project was huge and we couldn't subtract the reflection of the mirror manually. The second problem was the storage. When we designed when the pipeline finished first time, we found, because we are creating for each exposure different PSF, even the DPAD team couldn't support me. Then I had to redesign the pipeline to use less storage. Another challenge was finding the central coordinate of the saturated star, because I was using the saturated star for create the outer part of PSF. And the Gaia catalog, the central part of Gaia catalog is not completed. I found a methodology to find the central coordinate of these stars. Then another big problem, big challenge for me was sorting the brightest star for creating the outer part of PSF. Because in J+, I had broadband, narrowband, and medium band. And sometimes in narrow bands, emission and absorption occurs. I couldn't use the broadband filters magnitude like the Gaia magnitude to sort the stars. I had to find the algorithm to sort each star based on the different filters. And the last problem was, if I back here, you can see when we were masking the reflection of the mirror, we found we are masking the spike of the stars, while the spike is a part of the PSF, and it has to add it to the final PSF. And then I add a polar plot option to GenoAstro, and fortunately I could publish a paper regarding the polar plot, regarding this option is added to GenoAstro, and you can see I could add the spikes to the final PSF. And then after tackling all of this problem, I checked how PSF depends on filters, time, position, and how it will affect the sky map. And finally, we checked its effects on nearby object, which is shown here, how much subtracting the PSF, it will affect the surface brightness of this galaxy, NGC 4212. And when I obtained this map, it was interesting for me because here it's just 1, 2 stars subtracted. But you can see this star is out of the field of view. But this scatter light comes and cover whole the image. And it even affects the central part of the galaxy. Okay, the third challenge is address. And let's go to the final problem and to see how we could fix this problem. As you can see here, my main focus during my PhD was studying these structures. But these structures, the merger structures, they have different shapes and lifetimes. And in my project, it was 14 galaxies. I had to draw all the polygons by hand. Imagine, and even Elizabeth Sola, she had to draw all of these polygons by hand to extract the main body of the galaxy from these structures and halo. And in some cases like this, if you have 100 of the galaxy, you should spend half of your position time just to draw these polygons by hand. Then we're trying to develop an algorithm to extract these structures from main body of the galaxy. And fortunately, we have Arrakis, and I'm part of the Arrakis, and Arrakis would help me to extracting these structures from main body of the galaxy. First, because they are going to observe 80 minor merger galaxy. And the other hand, they are simulating 100 galaxies with realistic condition. This realistic condition would allow me to found what is the relation between the stellar stream shape and the dark matter and the shape of the all of the realistic condition like dark matter. And I use exactly this image, but without any noise and PSF. This image is created by Yves Revas. Thanks to him, I started developing this algorithm when I was in Geneva Observatory, and I've used this data. And as you can see, after obtaining azimuthal angle of this simulated galaxy, we saw the gradient of the azimuthal angle could allow us to extract the spine of these merger structures, merger remnant structures. And you can see in a preliminary result, we could extract the spine of all of these structures properly. Even this one, it's really faint. It's about 42 mag per arc second squared, its surface brightness, and you can see we could easily extract the structure. This algorithm is still under the development. Now I am trying to use the gradient of this azimuthal angle to grow all of these structures and then extract them exactly in which part the color, the gradient colors is stuff. I'm going to use this methodology to extract these structures from the main body of the galaxy. This algorithm is not just useful for the Arrakis J plus and J plus. With new generation of the telescope like JWST, Euclid, with and LSSC with big data, we need the tools like the new tool to allow us to study the merger remnants in more details. Until here, I just showed all of my results, and I did by myself. And now I want to show you all of my product of my research. I could publish 4 papers, 2 of them are referred, and then it's as a first co-author. And then I have many other papers as a collaboration with other groups like Lights and collaboration with David Martinez. And then another of my work during my PhD is I'm a developer of the GenoAstro. And as you can see, I'm the 3rd co-author, and I'm the active developer of the GenoAstro. And I'm trying to go before the Raul, I hope so. I'm just kidding. But it's impossible. And then all of my project is reproducible because it's written in managed, and it's if you want, you can just go to my archive and just press the link, clone from my GitLab all the project, and reproduce all of my work. And thank you very much for being here, and thank you for your attention. Thank you.
Thank you very much, Sepideh. Very nice talk. Questions? Yes?
Thank you so much. Oh, I don't have voice. Thank you so much. Very nice presentation. A lot of work. Now you have been working very hard these years. It got my attention, this new software that you are developing to detect these substructures in the stellar halos. And I was wondering whether you have tried some of the publicly available image segmentation software that is out there, like with the typical software that detects things on images, like this is a dog, this is whatever. You can actually use those kind of software.
It's my plan. First, I'm gonna develop this algorithm because when I send the Alba paper, the referee exactly recommend me to try the other software to see can we extract all of those merger remnants by their work. But I found all of the code is written in Python. And while I'm in this, let me go because I didn't have to show you all the details I put in my last slide. And because for developing all of these images, I need to work pixel by pixel. The Python was really slow and took a long time for me. First, my main purpose is developing this algorithm, and then compare with other tools. Even I'm planning to learn AI and machine learning tools to compare with all of them to see which one can work properly. But as you can see here, I have to work with all of I just show one step of the work, but I work with each pixel several times. For example, to excluding when after obtaining azimuthal angle, I had to calculate the minimum maximum of each pixel. Then I found the false detection in some cases for excluding all of this false detection. I use this algorithm, the mountain and valley algorithm. And when I tried all of these steps in Python, it was really slow. And due to this, I developed it in C.
Because Python is not optimized. Like if you go pixel by pixel, that is going to be a loop inside another loop.
Exactly. And for developing this project, this algorithm, I had to work pixel by pixel. I use each pixel as a main pixel, and I consider all the surrounding neighboring pixel for developing this algorithm. Due to this, I couldn't develop this algorithm But my main focus is in my paper. I'm gonna compare with other tools.
Even some PCA analysis or something like that could help you to recover structures of certain sizes. And that would be less costly computationally speaking. No questions? Carla?
Very nice work. I really
Thank
like
you.
your presentation. Thank you. So I want to return a little bit to the galaxy Alba, and then when you do the comparison, the why you are not having these oxygen-free lines, for me it was not clear how do you compare the other example for the galaxy that you say that for this galaxy, when you compare the two examples, you see that you try to look for another galaxy, similar properties that Alba?
Not similar property. They're just my main focus is obtaining the stellar population of the stellar stream tidal test, not the same story of the Alba, because Alba is the major merger. But in my analysis, you saw I have the many other objects, even some of them are minor merger.
Yeah, because the example you show is look like very extreme emission line galaxy, probably like AGM, because this is, I don't know if the way to the you say that the properties, I don't know, it was not clear for me. How did you put the example for you? What you don't expect this oxygen-free line?
In here.
This maybe
in this case, yes.
in the example, exactly how this example. So how do you conclude with that example?
I didn't.
Well, it's just only. I don't know if you understand my question, probably.
You are telling why I didn't continue this project, yes?
Yeah, why did you refer to that spectrum in comparison with Alba galaxy? Or this just an example?
I don't get you.
No, I think the question is more. So she detected some signal that looked like oxygen free.
Yes, here into these two, and because it was aligned with the manga, it grabbed our attention. And due to this, I went through the detail of just these two areas, which is shown here, to just focus in two high resolution or three areas. And
So Hannes Borberg was the first hypothesis when they discovered the signal.
yeah,
But then the signal was an artifact.
Okay.
It's an example of discovery. You don't expect something first, and then you see
Yeah,
like
I
there's a
think I
problem.
this prediction to just conclude how all those two regions was.
Yeah, I think
created.
my confusion was the connection with this example here.
This is sorry, maybe I should
connection,
improve
my
my
confusion.
explanation.
That's fine.
When I reached this point, I didn't know what is happening for this galaxy, why I cannot see the other line. Because the first star forming component is petrol 5H beta. And then due to this, I was wondering why I cannot see the other lines. And then I said, okay, let's search in the other paper to see, can I find any other galaxy? They have just O3. Then I found Honeywell object.
Yeah, this is there was my confusion because this I think is an AGN. Because you had neon 5 and helium 2.
Yes,
But the
yes.
reason was like my confusion, but yes.
Yeah. And I should mention that the Alba is the safer two galaxy. And
okay.
yes.
Okay.
And I think I didn't mention it.
No.
Sorry for
That's
my
fine.
bad. And due to this one, I was trying to just predict what is happening there for Alba. Yeah.
And I have another question.
Yes, of course.
Did you find any trend with the different merger when you do the polygons to see some about more the structure of these mergers? Because I think sometimes you develop by hand, probably you find something like interesting.
With these 14 galaxies, no.
Okay.
But I think in future, with more galaxies, maybe we can find some relation between the shape and properties of the galaxies. Yeah. But now I just had these 14 galaxies because my main concern was to just extract galaxy which observed by 54 nanobands. Yeah.
Okay.
I hope in future I answer
Yeah,
your
yeah, that's
question.
interesting. The TV because also the connection
Yes,
with the
yeah.
organization.
Exactly.
More questions?
I have several minor questions, not on the method, not on the results, but on the presentation. So, okay.
Okay.
First, please put numbers on the slides because it is much easier there for the question part of the
okay.
presentation. I don't know if the number is hidden below.
No, it doesn't have number.
Yeah, put numbers, it's easier. Then, in the slide where you show the manga spectrum of one of the galaxies.
Manga spectrum of the
This one,
other.
yeah, the next one,
This one?
the next one. This one. You say there manga undersample. It's better to say manga resample, something like that. Because
Resample?
undersample sounds like you are dropping pixel. Maybe resample to the JPEG resolution.
Is it resampled or is it convolved with the with the figures?
It's resampled. I didn't convolve.
Okay.
It's resampled.
Okay.
This would be this resampling is undersampling. It's bringing it down to from the resolution of manga.
Resample covers both.
Yeah,
It covers
exactly.
undersample or
Yeah.
oversample. But if you say undersample,
It's like the convolve.
in fact there is a typo there. But if you say undersample,
thank you.
looks like you are
Can
dropping
I
something.
take notes?
Instead of just undersample to a
I don't
quartz
have any.
resolution.
Well, this is recorded, right? So we can later.
Right.
Yeah.
No, it's okay.
Yes, when you compare the regions with SDSS,
In manga here or here?
this one, that you say here that in the Z band, SDSS is different because of the
Reduction.
band reduction, and also in legacy survey you say band reduction. Don't say that. You're throwing them under the bus. You can say that their reduction is not optimized for low surface.
Okay, okay, okay.
And finally, in one of the slides, you show the first fit with Seagal for one of the JPAS galaxies, not the Alba one, but all the others.
This one?
No,
No, not the Alba.
the others.
This?
No, the S-infinity.
I
You
don't-
show the spectrum with the Seagal model
No, I think
for the
I think
JPAS
it's-
galaxies. No, go ahead.
Go ahead.
Ah,
There is a slide where you show the typical Seagal figures.
Yes, I will
This
say
one?
when I see it. No, continue. This one.
uh-huh.
This one. You saw there the chi-square 0.17. This is too low. This is probably because your photometric errors are overestimated or something like that. Maybe just don't say what is the chi-square. Because it's probably just the overestimated photometric errors. It should be around 1.
You mean I shouldn't mention about this emission line?
No, because the emission
No,
line
the
is
emission
there
line is
even
real.
without the fit.
Yeah,
That's
this
not-
line is real. It's just that.
Oh, I
you get a
should
very
just
low
mention
score.
about chi
Yes,
square.
don't say it.
Okay,
But
The focus isn't the fit, the focus
Yes.
is the emission line.
yes, exactly. Thank you.
More
Well,
questions?
since we are on the presentation side, there's 3 things that caught my eye. Start from the most basic one. At the beginning, basically at every transparency, you show the structures and you say this beautiful structure, this beautiful structure, this beautiful structure. First time is perhaps okay. Then I would just say the structure.
Okay,
Then there was another one which, oh, right. Oftentimes, I noticed that there's a couple of times where you do it, you show a slide, go to the following slide and go back. And then you go back, forward, skip, because you never do it. This just causes, it makes people seasick. And it's distracting because at some point you start going in one direction, you go back, go forward, and that just doesn't work. It's a waste of time for you, and it loses people's attention. Third, and it's the most important thing, you're treating the presentation as if it was the important thing that you want to speak about, and it isn't. You're speaking about your PhD project, so what you're saying is what has to be the focus. If you speak half of the time with your face facing there, first, we cannot hear you because your voice goes the wrong direction. You're not looking at us. You're missing our attention. You are drawing our attention to the screen, not to you.
Mhm.
You are the center of the attention. The screen is a support to what you're saying. So don't use your point. I understand it. When one is young, still has this, it becomes your Linus blanket to have the pointer. Linus blanket, everybody understands the fuck. Anyway, it's your safety net to have your pointer staring at the presentation like, this makes me feel safe. But the thing is, you're talking to us, you're not talking to the presentation.
Yeah.
Right? So only refer to the presentation when you need it. Trick, I'm not sure if you have it, but if you are mirroring the presentation,
Yeah, I have it.
you can just look at the presentation there and then look at us. So basically you only have always one direction. You never have to turn back. And you only point whenever it's needed.
Okay, sure.
You can also move the mouse with the mirror thing. The mouse is a nice way to.
And you can use
also for the remote people.
Right. Yeah.
Okay, sure. Thank you.
First one?
Thank you for the presentation. I like it.
Thank you. Thank
For
you.
me, it was quite it was fairly clear. So in that respect, I think you already have it in place. I just want, well, I wanted to comment. This was already commented, so I will go into this. I just want to comment. It's a comment that regarding the Alba galaxy, I fully understand that it was a disappointing result.
For me.
Figuring out that you didn't, that was not actually the O3 emission, but but nevertheless, this is a very relevant result, and it shows that you have been doing rigorous work and a critical work on your data. So, and again, the PhD, I can remember a thesis of one of my colleagues that was on finding an exoplanet through the transit method. He found one, but even if he didn't, it's a result. So, yeah. So just to comment that was an important result for others, and for particular for us to pay attention to the signal, to try to sort out this, or to flag these areas in the image. And yeah, I think most of the other questions were already addressed. My only point maybe is that the corner plots that you show, I get a little bit lost here. I must confess, it's not my field of expertise, but for me it was not clear.
Yeah, maybe I should explain more detail. In Access, I have all the,
First of all, I cannot read what is there. And another last point. I don't know if you didn't describe J plus and J pass, because because of the audience,
Yes.
or whether you are thinking on doing that for the thesis presentation. I don't know.
Yeah, I have to. I think.
Maybe it's not needed even for that. But I comment just for you to consider.
You introduced JPass, and you had the slide with the J plus coverage when introducing the PSF.
Yes. Yes, I have this, but for J-plus I explain a little bit, but for J plus no. I just mentioned about 12 people.
And just to be sure that
After this, yes, this one.
I think perhaps I would move the description of the surveys at the beginning of the introduction because that's the general context.
Yeah.
Yeah.
So you can tell them, okay, everything I'm going to do after this is based on data from these two surveys. You present the surveys and then the rest of the presentation you don't have to come back to describe the survey and everything. It's going to be easier.
Yes, you're right. Maybe I should bring these two slides to the first of my presentation.
Yep.
I just saw one more thing on the slide presenting JPass. Can you go there? This one. Effective wavelength 14 nanometers. No, it should be effective wavelength resolution.
Ah, okay. Thank you.
Okay. Questions?
This was a very nice talk. Thank you. My comment is about how to finish the presentation, because I don't know if this depends on the university rules, but I understand that you have to finish reading the conclusions.
Really? Sorry, I've never been in a Spanish PhD difference. We don't have PhDs.
Maybe I am wrong, but this is something that you have to do.
I think you have to do it. I don't know what's the rules in Unifar, but
That's the point.
I should read it in Spanish?
No, but you should say something like, with the permission of the panel, I'm gonna read the conclusion.
Okay.
So you have to present everything regarding the application, the master meet and everything. But then at the end, you need to finish with one slide or several of them, few slides, reading actually the conclusions. Not saying but reading the conclusions.
check if this is the rules of Unifar.
So, my point here is check it.
Okay, sure, I'll check.
According
Thank
to
you.
the
Thank you. I didn't know about it. Thank
And
you.
for that, do they put the text in the slide?
Yes.
And you have to literally read it.
But you have to read looking at that.
Okay. There are no comments or questions. Thank you very much, Sepideh.
Thank you.
Good luck.
Thank you, everyone, for being here. Thank you.
You're welcome. Don't miss the main talk on Friday.
Okay.